stars. So basically, like the bigger mass star, the center mass will be close to that one. So it depends on the two masses of the star where the center mass is. And for it to be eclipsing, basically the line of sight of the observer has to be on the same plane as the orbit of the star.
So in order to analyze eclipsing binaries, we can plot the brightness that we see as a function of time. So as time passes, we can see the light actually change that's coming from the system. And you can see this video will play. So you can see as one star passes behind another, it dips in brightness. And whichever one has the bigger dip when it's behind is actually the brighter star. And
Okay, so what can we learn from the light curve? Well, actually, there are a lot of things we can learn. We can find out the brightness of both stars and which one's brighter, like he was saying. The bigger dip that we get in light curve graph shows which star is brighter. We can also find the rotational period of both stars.
so there are a few different types of binaries. You've got contact, which is the one up at the top, and it looks like a peanut sort of shape. The stars are actually so close that mass is flowing between the two, and they share mass and sometimes act almost like a single star as they orbit. Then there's semi-detached, where one star is actually stealing mass from another star, and it forms this ring of like gas and plasma around one of the stars. And then you have detached, which is just two stars. They're kind of far apart, but they orbit. They're not the center of mass. And then you've got various distinctive light curves for all three.
And so our star that we studied was B0497 Andromeda, and that's located in the constellation Andromeda. You have up here the coordinates on the celestial year for that star, and the magnitude, which is 14.7 to 15.5. And so in the middle right here, with this little square, that's our star, and then we use this as a comparison star for finding the light curve, and then these two stars as our chart.
The reason that we had to compare the stars is so that we can have sort of a background against which we can measure the light. And so to get the clearest image of our star, we had to take several images in different kinds of frames, called bias, dark, flat, and light. And you use those to find what the star actually looks like, getting rid of random interference that comes from various studies.
And so one of the frames that we took was a bias frame, and the bias frame is taken with shutter close and no light comes in it. This is an example of a bias frame that we actually took on one of our days. It has no exposure time, and the purpose of it is to eliminate green noise coming from the telescope itself.
And then there's dark. Dark frames are also taken with the shutter closed, so that no light reaches the image or reaches the detector on the telescope. And this actually does have an exposure time, so that it can remove noise coming from elsewhere, like from heat and stuff from the surrounding.
And so another one that we had was our flat frames. And you take that basically by pointing the telescope at an even, like illuminated surface. And so in our observatory, that's basically like not like a whiteboard. And so we pointed at that, and basically that works to remove vignetting, which like if you take a picture and you notice how it's bright around the center and dark on the corners, and that's caused by like uneven illumination in the camera. Eclipsing works to remove that, and also dust particles that could be on the sensor.
So we take all of these images of our star and we take them in various filters of like indigo and visual on 2 separate days, which it would have been 3 separate days, but our 3rd day there must have been dust or smoke or something that messed up the readings with the telescope and made the data unusable. But then we entered all our images into the program and it analyzed the differences in these images that are taken over time, and it plotted them into light curves.
And so these are some of the light curves that we got. Over here on the left is from the indigo filter, and in the middle is from the red filter, and then on the right is the visual filter.
So our star is a contact binary, and we know that because of this W shape in the light curve, which is characteristic of a contact binary.
And so what else can we find? Well, from that graph, we can find the orbital period of the 2 stars, which we found to be 0.3041 days, which is 7 hours and 19 minutes. And that's how long it takes for the 2 stars to orbit around each other.
We would like to give special thanks to TSU for providing us with this. We'd like to thank Dr. Marvel, Mr. Sawi, Mr. Gadaria, who leads the astronomy program here,